In this video, I will demonstrate how students can reach the flow state in the classroom. The lesson during which I've watched this happen centered around dimensional analysis, and my students were working on conversion problems. Yes, you heard it right. My students were doing basic math. But to reach flow in science class does require some prep work. So if you thought this would be a quick lesson tweak that you could implement, I'm sorry to burst your bubble here. Pun intended, as my lesson starts with an explosion in the fume hood involving a balloon that popped with a bang, frightening even to this chemistry teacher. Want to hear more about my lesson flow? Let's dive right into it. But first, we have to start with a definition. What is the flow state? Flow state is a mental state in which a person is fully immersed in an activity, characterized by a feeling of energized focus, full involvement, so no social media distraction, and even, dare I say, enjoyment. Exactly what you're used to seeing in your high school students while in the classroom, right? Flow is often described as a peak experience, like a chemical reaction reaching activation energy at the top of the potential energy diagram. During this peak experience, a person has self-awareness, is fully absorbed in the present moment, and even loses sense of time. Better keep that analog clock in the classroom. If only we could reach this peak experience, this flow in every lesson. But how can we at least up the chances of it happening? In other words, how can we get our students into the flow state? In order to reach the flow state, we teachers need to impart knowledge. Whoa, this may look familiar to some of you, the next generation STANYS standards. So knowledge refers to the actual content we are teaching, the so-called disciplinary core ideas. In other words, what students know or ought to know. Next, we need to impart skills. Again, referring to the next-gen science standards. These would be the cross-cutting concepts, giving students the framework to connect knowledge from various disciplines. In other words, how students think. The third component that would facilitate our students to reach the flow state is abilities. NGSS refers to these as the science and engineering practices, which basically means STEM students learn by doing. In other words, what students do. Taken together, these flow components go by the acronym KSA and enable students to focus effectively and immerse themselves in the educative task at hand, possibly leading to a flow state. We are now ready to start with 3 lessons that encompass these 3 KSA components. Let's flow into them with a bang. So in order for our students to reach that flow state, we have to start with the first component, which is knowledge. Knowledge basically relates to the content, what students know. So I'm showing you here the next generation science standards, and my lesson revolves around the standard High School PS 1-7, using mathematical representations to support the claim that atoms, and therefore mass, are conserved during a chemical reaction. This involves students learning how to convert between one unit and another. Let's go to the lesson. The first lab that I do with them to impart this knowledge is called mole stations. It's a really fun lab. And the purpose of this lab activity, as is stated here, is for students to become more familiar with the mole quantity and to determine how this mole quantity is related to molar mass. And they will also do other conversions, not just from grams to moles, but also to number of particles and even liters. They will also use one other formula referred to as the percent composition. So they will complete 8 different stations. And the stations really can be completed in any order that they wish, whatever is most convenient for the students in the classroom. They start off with how much aluminum is in the foil in this particular document, and then they delve right into how much carbon dioxide is produced in this balloon. Very simple baking soda and vinegar reaction where they are actually letting the carbon dioxide captured in the balloon release, and then they calculate the mass difference and convert the mass into moles and then into liters, assuming standard temperature and pressure conditions. Another station is how much copper sulfate is in the beaker. They decide how much they want to put in a glass beaker or on the weigh boat, and they measure it and do some conversions. We've got additional stations, including a Snickers bar. You can actually hand them out the Snickers bar, or a little less interesting perhaps, have them look up the information online without any Snickers there, but that's no fun. Another station is chalk. They can basically write on a piece of paper all their group members' names and possibly addresses on that paper, which of course loses some chalk. And if they re-weigh their chalk pieces, that will result in a loss of some chalk. And then they can figure out, how close is that amount of chalk that was lost to a mole? They can do some other conversions, determine how many chalk particles they actually lost, etc. Another station involves chewing gum. How much sugar is in the gum? Chew it before, measure it before, and then after. And of course, the weight should be less because all the sugar dissolves out of the gum. And they can see, okay, is there a mole that we actually have lost as a result of chewing the gum? Station number 7 involves an iron nail. And they weigh the nail, see how many atoms are in there. Is it a mole? The last station involves Oreo cookies. And the Oreo cookies can be regular and double stuff. You can throw in a whole bunch of flavors if you wish. And then they're going to scrape the cream away from the cracker, take some measurements, and figure out the percent composition of the regular Oreo cookie compared to the double stuff. Is it actually double in terms of the cream? Does that also mean it's double in terms of percent composition? Well, that's for them to figure out. This mole stations lab probably takes about 2 cells to complete, and then you finish that knowledge component of getting into the flow state. That brings us to our second flow component, skills. The Next Gen Science Standards refers to those as the cross-cutting concepts, how students think. This second lab is meant to provide students these skills. It's titled, Let's Pop That Balloon. Let's. The purpose: in this lab, you will determine the stoichiometric amounts of hydrogen gas captured in balloons as a result of adding various amounts of magnesium ribbon to a controlled amount of hydrochloric acid. They will be working with 3 molar hydrochloric acid, and I actually do this lab as a demo. So first, students set up a balanced chemical equation. They determine, with my help, what kind of reaction it is, whether it's decomposition, combination, single or double replacement. They come up with the mole ratios, 6 of them, based on that balanced chemical equation. And then I actually choose one of the 4 reactions to demonstrate in the fume hood. And this one is highlighted here as demo number 2. It involves 47 centimeters of magnesium ribbon that they will weigh, and then they can convert that mass into moles, and subsequently they can figure then out, based on stoichiometry, whether the magnesium or the hydrochloric acid, there's about 0.1 moles of HCl in the flask that I demo, whether it's limiting or in excess. So lots of conversion here that hopefully will expand their skills based on the knowledge that they received during that mole stations. Next, they will actually manipulate the balloons that are above these flasks. So you should simply click on the balloon image, and then you can increase or decrease the balloon size to show how much hydrogen gas that these balloons actually capture. So based on the demonstration of flask number 2 that you saw early in the video, where we actually put 47 centimeters worth of magnesium ribbon inside the balloon, put it over the mouth of the flask with already the hydrochloric acid in it, let the reaction happen, the students can then really observe, is all the magnesium getting used up, Is there any left over? And that gives them already a little bit of a hint what's limiting, what's in excess based on that observation. And then, of course, the fun part is to explode the hydrogen gas. So they then finish with this activity, which also completes the skills component, with defining some vocabulary terms and answering the following question. Explain, using all the vocab terms below, why magnesium is considered the limiting reactant in the above reaction carried out in flask number 2, which I demoed. And relate this to the amount of hydrogen gas produced. What measurement did we actually not end up taking to be able to determine the actual yield? Compare that to the theoretical yield. The third activity that I do with my students centers around that last flow component, abilities. And it basically centers around what students can now do. They have now some background because I gave them the knowledge. They've gotten some skills because they've practiced some more with the knowledge I originally gave them. And now we're going to take it to the next level, abilities. This may seem like the most dull worksheet you can ever imagine. Let's take a look at it, okay? I'm showing you here the actual New York State chemistry reference table with all the different units. The tool that I give to my students, how to convert one unit to another through dimensional analysis. Some very simple basic starting examples. And then a whole bunch of practice. Let's look at the units that I'm releasing upon them. Grams to moles, moles to grams, but then also some units that I have not even covered with them yet at all. So we're seeing here atmosphere to kilopascal and the reverse. Even kilojoules to moles based on heats of reaction. Have not taught them this at all yet. The second and last component of this worksheet revolves around metric conversions, and it's basically a review revolving around scientific notation and playing around with that. Let's scroll through the kinds of conversions that I'm having them do here. We're going from kilograms to grams, or to milligrams, to micrograms, picograms, basically all involving a multiplication with a factor of 10. It is during this third activity, this worksheet, which looks kind of dull, that I noticed my chemistry students in both classes totally reached the flow state. They were completely immersed, lost track of time, seemed to enjoy themselves, and practiced their abilities based on having gotten some skills and background knowledge. And I remember when we reached the end of this lesson, the bell rang and several students poked up their head and said, "Whoa, that lesson just flew by." I hope you enjoyed this lesson, during which I shared what I do with my students to enhance the chance of getting them to reach the flow state. All the lesson materials are in the description below, including keys to all of them. And I hope to see you in the next video. Thank you for watching. Bedankt voor het kijken en tot ziens.